You have to name it, right?
You have to name it. So you want to give it a try?
Yeah.
Go ahead.
Iron phosphate.
Iron.
Phosphate.
Okay. Do you have a different name?
No.
Same thing? Anybody have anything different? So everyone agrees that this is iron phosphate? Yeah? All right.
Double check again.
Let's look through the flow chart and make sure we got it right.
All right, yeah.
So is it ionic or molecular? Do you have something?
It's ionic.
Ionic.
Ionic. How'd you know?
Because that's iron.
Iron.
Because of the metal. Okay. Is iron have a fixed or a variable charge?
Variable.
How do you know?
Because it's in transition.
Transition metals. Okay. So then the name should look something like this, right? So what are we missing with our name?
Yeah, so instead of phosphate, sorry, it's phosphate.
Well,
Maybe.
that's not true. The phosphate is correct. What else are we missing? The charge, right? Iron has a variable charge, so we need to put the specific charge right here. 3.
So iron 3 phosphate.
Yeah. So this should be iron 3 phosphate. How did you know it was 3?
Because
Whoever.
phosphate has a
Negative
negative 3 charge.
Right, because we know that phosphate has a negative 3 charge, so the iron has to be plus 3 to balance it out.
How come, and I've noticed this, they don't write it, they don't write PO4 3 minus. Why is it when you put it together, you don't write the charge, but on other ones, you do write the charge?
Yeah, when we're talking about the ion by itself, we always write the charge, like up here, right? But when they're in formulas, we don't put the charge up there. Main reason for that is it's not, it's no longer really clear what it's talking about. So let's say, for instance, that I put PO4 3 minus up here. What that looks like to me is that this whole compound is 3 minus. Right? So by leaving the charge off, we can assume that everything balances out properly. If we do put a charge in there, it's because the overall compound together is going to have a charge.
So it's always, whenever you're combining two things, you remove the charges.
Yeah, if you have a neutral compound together.
And in order for them to stay together, it has to be neutral.
That's not entirely true. You could have a compound that is not neutral, that is plus or minus 1 overall, like they don't totally balance out. But then that would need to be shown.
But for all the ones we're doing, we're just going to assume that they're going to be neutral because you're wanting us to change
Yeah.
the
Right.
name.
Right. Okay, let's do one the other way, and then we'll move on a little bit. So let's take copper. And let's look at copper 2 hydroxide, and let's see if you can come up with a formula for copper 2 hydroxide. For those of you without a periodic table, what's the symbol for copper? Cu.
CuOH2.
Like this?
Yeah, it's on the outside.
Okay, you make it something different? Everyone's in agreement with this one?
I would write it CuOH2 without the front.
Without the parentheses, so you would write it like this? Okay. Anybody get something different? Anything else? Between these two, that's everyone's ideas? All right, so why or why not with the parentheses? So you want to give me a reason?
Because like if you have parentheses, it only does it to that one, but if you don't have parentheses, it's like the whole compound.
All right, well, kind of. It's actually just that flipped. So when we put the parentheses, that means that it's two of these whole OHs. When we don't have the parentheses, then the two is really only applying to the hydrogen and not to the oxygen with it. So in that case, this is not the right way to write this because this is telling us that we have a copper, an oxygen, and two hydrogens. And what we really want is a copper and then two oxygens and two hydrogens, the OHs all together. So this is the better symbol for copper hydroxide. How did you know you needed two of them?
Because of the, copper.
Yeah, copper is a +2 charge here because it's given that it's copper 2. So we need two of the 1- hydroxides to balance it out. So this is great. Sounds like you do know these polyatomic ions pretty well.
So if it was copper 3, it would be CuOH3.
Yeah, right.
Okay, 'cause there's 3.
I know one like it isn't.
One that what isn't given? Okay. Yeah, I mean this is pretty much all the variations. You've got these, and then you've got the molecular compounds, and then you have the ones that don't take a number. So we can look instead at, let's say, SiO2. What do we name that one? Who wants to give this one a try? Silicon dioxide. Yep, silicon dioxide. How do you know that was how you should name it?
Because both of them were sixth place in the periodic table, so considered. So it's like metal, it's like a.
It's a semi-metal or a metalloid, yeah.
Yeah.
Yeah, which gets named like a non-metal.
So I just assume it's a non-metal pretty much, so then
Mhm.
in that case, since it's two combined together, then you have to put the prefix.
Yeah. So we need the prefix because we're naming this like a non-metal, so silicon dioxide. All right. And then the other, let's see. Try this one. What can we name this one? Anybody feel like they got this one? Yeah. There.
Beryllium chloride.
Beryllium chloride. Okay. Everybody get something different? Beryllium. Tetrachloride. Okay, anything else? All right, well, let's think about this. Why beryllium chloride? What brought you to that?
Because it's ionic, it has a metal and non-metal.
Okay.
And then so you leave beryllium alone, and then you just change the CO to the chloride instead.
Okay. Thanks. And why tetrachloride?
I
Anybody
was
else?
thinking that there was a +2 charge beryllium and a -1 in chloride, but there was 2 of them,
Yeah.
so that would make 4
For what?
chlorides. No.
Oh.
Okay.
Okay. Yeah. Why not number in parentheses here after the beryllium? Or should we? You think so? Why? Well, where is it on the periodic table? Can I find beryllium?
Because it's not a considered transition metal.
Right. So it only really gets that 2+ charge.
Right, exactly.
Yeah. So that's the better name here. Beryllium chloride. It's an ionic compound, so it gets named as an ionic compound. And we don't put the charge in parentheses because it's not a variable charge. Now, if we want to be really confusing, beryllium chloride is actually a molecular compound, but we won't really get into that because we can think of it as an ionic compound for naming purposes. Okay. All right, so keep working on this, keep practicing. Sounds like this is going pretty well. I mean, definitely hearing a lot more good answers than what we did last week when we were first starting it. So that's great. Keep learning it. Make sure you know those polyatomic ions and keep practicing these naming rules and getting used to them. Couple little things we have to finish up talking about these compounds that we haven't gone into. One is the structure and 2 is the forces among molecules. We're going to skip a part of the chapter about shapes of molecules. So you'll notice that's not listed under the readings or the problems for that particular chapter. It is 4.7, so we're going to skip right over that one. But we are going to talk about electronegativity and bond polarity in terms of covalent compounds. So the next things we're going to talk about pretty much exclusively apply to molecular or covalent compounds. We'll say covalent compounds. So we're talking about molecules that with covalent bonds. And the other part of that is I haven't really told you the whole story. So we talk about ionic compounds with metals, covalent compounds with nonmetals, but it's not really that simple. The fact is that there's a whole range, depending on where the electrons are in relation to the 2 atoms. If the electrons are totally over on one atom, and that atom has a negative charge, and the other atom has a positive charge, that's what we call ionic. But then there's a whole continuum of where those electrons could be shared a little bit, shared a lot, shared perfectly evenly, and actually it matters how we talk about those electrons being shared. So let's go back to our simple covalent compound of hydrogen, dihydrogen H2. You've got 2 hydrogen atoms that are sharing 2 electrons. And in fact, if we kind of draw a picture of that, we could think of like an electron cloud with the 2 electrons in it. And those electrons are shared perfectly evenly. Both sides are hydrogen. There's no reason for the electrons to be on one side or the other. So they're distributed evenly across the compound. Now let's contrast that with something like HCl. A similar compound, HCl, also a covalent compound, hydrogen singly bound to chloride. But now the picture of the electrons in that bond is quite different. Instead of the electrons being shared evenly between the two elements, the electrons spend most of their time over around the chlorine and less time around the hydrogen. So we could say it's, off center a little bit over here. And the electron density or the electron cloud is actually more over by the chlorine than it is over by the hydrogen. And so we have names for these, for the effect of these. Because what happens is when you have the electrons more on one side, that side becomes more negative, and the other side becomes more positive. So some negativeness over by the chloride, some more positiveness over by the hydrogen. It's not really like a full charge like an ion. I'm just saying there's kind of more of a positive field on one side and a negative field on the other side because those electrons are kind of lopsided and they're over on one side more. We call that a polar bond. Polar meaning having poles, like positive and negative poles. So in a polar bond, you're going to have a negative side and a positive side. And the opposite of that, when you don't have that difference, is called a nonpolar bond. And there's a nice picture. Well, we'll get to that in a second. When we draw this then, or when we want to express this polarity, we don't really use full positive or full plus and minus symbols because that would imply a transfer of electrons. That's what we use for ions, pluses and minuses, like all the stuff we've just been talking about. So we use a special symbol, a lowercase delta, Greek letter delta. Delta means a little bit of a change. So a delta plus is a partial positive, and a delta minus is a partial negative. So we're saying here in this molecule that the hydrogen side has a partial positive charge, and the chloride side has a partial negative charge. Again, just applying to the uneven sharing of those electrons. The electrons get pulled more to the chlorine, pulled away from that hydrogen, and that changes the electronics of the substance so that you have some negativeness over by the chlorine and some positiveness over by the hydrogen. Okay? The other name that we'll sometimes see for this is a dipole. Whoops, I'm sorry. A polar bond is, so we say that it has a dipole, meaning two poles, a plus and a minus pole. The dipole is actually a quantity that can be measured in numbers, whereas polar, nonpolar is more like a qualitative assessment of just does it have that lopsidedness or not. We can actually predict what kind of compounds will make these polar bonds versus these nonpolar bonds, and they have consequences in how the molecules interact with each other. So to do that, we use a quantity called electronegativity. And we're going to define electronegativity as the ability of an atom to pull shared electrons toward it. So we're not talking about it's just ripping, we're not saying like it's ripping electrons out of the air and attracting to them. We're saying when this molecule is in a covalent bond, something that is electronegative, an atom that is electronegative, will pull those shared electrons more toward it, leaving this kind of lopsided nature that we call a polar bond. To find out the electronegativities, we can actually look that up on a table. Do I have it set up? Let me, I have to log back in here, I think. It's gonna let me get the book. Nope. Let me pull these pictures from the book here. Okay, or not. If you've got a book with you or you're following along, this is page 149. If our internet is fast enough to actually do it.
So it wouldn't just be the atom that has the most electrons in its valence.
It kind of is, yeah. It's a little bit different, like how you compare fluorine and chlorine, for instance, because those would have the same, F and Cl would have the same number of electrons in their valence shell. So we do need some numbers. While that's loading, let's look at a couple. So chlorine is 3.0. Hydrogen is 2.1. If we go back up to our example here. So if you've got 2.1, 2.1, there's no difference in electronegativity, hydrogen and hydrogen. And so you're going to have a perfectly evenly shared bond. But when you have 2.1 on one side and a 3.0 on the other side, the electrons are going to get pulled toward the 3.0. And now you have this lopsided polar bond. Still waiting, huh? Reload it here. There we go. All right, there we go. So we're going to 149. Oops. Oh, I got the wrong edition of the book. Okay, we will find it in the other edition here. Not 149. Uh, 189. If you have the newer version. Here's our little table, so I'll pull this up and put it in the notes for those of you who don't have it. Okay, so here's our electronegativity table. You can see we only really deal with those elements that are shown here, so we're kind of missing the middle ones. Those all have really low electronegativities. You can see the hydrogen kind of goes over here because it has the electronegativity of a nonmetal, kind of fits more in with the nonmetals as we know, even though it's really on group 1 with the metals. But you can see the things I really want you to know here, you're not going to have to memorize any of these numbers, but you need to know these general trends. That as we go to the right, as Deborah said, we increase electronegativity. So in general, if you're comparing two atoms, left to right on the periodic table, the one on the right is going to have that stronger pull. Then if you're looking at the column, the smaller ones, the ones near the top, are going to have that stronger pull. So what a lot of people like to remember is you can think about fluorine. Fluorine has the highest electronegativity. And then you can think of kind of everything else going toward fluorine. And the closer it is to fluorine, the higher the electronegativity. The exception being hydrogen. So if you're going toward fluorine, that means you're going up and you're going to the right, and that's when your electronegativity is increasing. Knowing that, we can make some conclusions about whether or not bonds will be polar. For instance, a carbon-oxygen bond. Would you expect a carbon-oxygen bond to be polar? Just looking at the periodic table?
Yes.
Yeah. So which part would have the partial negative charge? Where would the electrons go? Would they go to the oxygen or to the carbon? The oxygen, because that has the higher electronegativity. So we would expect in a carbon-oxygen bond to have a slight negative charge on the oxygen and a slight positive charge on the carbon. Now, when that difference becomes really small, like with carbon and hydrogen, we're looking at 2.5 versus 2.1, we consider this difference to be basically negligible. There isn't really a dipole moment or a polarity in a carbon-hydrogen bond. And so compounds made up mostly of carbon-hydrogen bonds are not going to be polar, are not going to show the separation of charge. There's a nice table also in the book that we can look at to kind of give us some guidelines on this. I like this picture also. And what we see from a picture like this is this idea of this continuum that I talked about. So we can really think of all interactions as a product of this drawing of electrons from their electronegativity. If the difference is really big, we actually call that an ionic bond. So when we have a huge difference in electronegativity, the electrons are entirely on one side and not on the other side, and we call that ionic, meaning that the electrons are completely segregated. And then on the other side, we have a non-polar covalent when they're evenly shared, like hydrogen, hydrogen. And then everything in the middle, above about a 0.4 difference, is considered a polar covalent bond. So that's still covalent, it's still shared, but it's shared unevenly. So you can see how there's a whole range here. It's not really that ionic and covalent are so different, it's that they're different parts of the same scale of how unevenly those electrons are shared. All right. Questions about that so far? So the other issue about that then is, I don't even think, as we'll see in lab today, yeah, the book doesn't really talk about this, but as we'll see in lab today, this is not some magical rule. It's not like something physically changes when we get to that 0.4 or that 1.8. These are just kind of buckets that someone has set up. What we'll see in lab today is a better way to determine whether or not something is ionic. Anybody see from reading ahead, what's a good way, or getting ready for lab today, what's an actual good way to tell if something's ionic or not? How can you physically test if it's ionic?
Two different ways.
What? Conductivity? Yeah, is that what we're going to say here? Yeah, we're going to actually look at the electrical behavior, because what does it mean for something to be ions? It means that you have individual discrete positive and negative particles in solution. So you dissolve an ionic compound in solution. If that solution conducts electricity, you've got an ionic compound. You've got ions there. If it doesn't conduct electricity, you don't have ions there. And it doesn't matter where it fits on that scale or what the differences in the activities. If you test it and it doesn't conduct electricity, we can't really call it ionic. You have a question? Yeah. And so that's really a better test, though we can kind of use this on paper to make some beginning conclusions about that.
So, like, would you say that, like, for example, when we're union, we're trying to find the charges so they can balance out? In essence, we really don't balance out them. I mean, just by looking at it further in more detail, I mean, it looks like one side is, like you were saying, like it looks like it's more. The
Right.
ions are, well, one side is attracted to.
Yeah, one side is than the other, but you will still always need an overall balancing of charge. So you can have positive and negative around, but you're never going to have like a jar full of negative ions. They're always going to have the positive ones to balance it out. So numbers of particles are still going to have to balance.
So
So the electronegativity difference is 0.3, it would be non-polar covalent.
So there would still be a slight difference there, but when we think about the overall behavior, we'd say that probably doesn't have a huge effect. It's mostly nonpolar. So now let's talk about how we use this information to make conclusions about actual molecules. One thing that we can talk about with this is what we call the dipole moment, which is just a way of talking about the overall polarity of a molecule. Let's take water, for instance. Structure of water looks like this. Again, we're not going to get into the molecular shapes part, but water is bent. It has a about 105-degree angle there. So water is made up of OH bonds. Is an OH bond polar or non-polar? We'll go back up to our chart and check.
Polar.
It's polar. All right, oxygen's a 2.1, or hydrogen's a 2.1, oxygen's a 3.5. So that's a pretty big difference in electronegativity. So these bonds are polar, and there's two of them. So each hydrogen is going to have a partial positive, and that oxygen is going to have a partial negative charge. Each of those bonds are polar. Another way that we can draw these is as arrows. We can talk about the arrows, well, they're really vectors, arrows, as pointing toward the direction of where the electrons go. Let me make a bigger picture here. All right, if these are our angles, then we can say, well, the dipole on the polar bond on this side, the dipole on this OH bond, is going to kind of look like that. The little plus side reminds us it's a plus there, and the electrons go toward the negative. And if we look at the other side, we should have the same magnitude dipole, but in a different direction.
So even if, like, I mean, I know that it's stronger, the oxygen's stronger, but,
Mhm.
but even if it has like two hydrogen particles, it's still, regardless, oxygen will still be the strongest.
Yeah, we're going to look at each individual bond first. But that's a good point, because that's what we're going to do next. Then we can actually add these vectors together to get the overall dipole moment of the molecule. That is it overall polar or not? So in this case, what we do is we kind of take one, and then we take the other one, head to tail, and we say, okay, overall this molecule is going to have a dipole in this direction. So the overall dipole of this molecule kind of looks like this. And we would say that not only are the individual bonds in this molecule polar, but the overall molecule altogether is polar. And we would call this a polar molecule. Now let's look at a different one. Another common molecule that's going to have a little bit different conclusion. The next molecule we're going to look at is carbon dioxide. Carbon dioxide looks like this. We've got a carbon in the middle and two double bond oxygen. And the shape of carbon dioxide is linear. It's all in a straight line all together. Again, if you want to know how to come up with these shapes, you can read that section in your book, but we're not going to focus on that for this semester. Now, is a carbon-oxygen bond polar or nonpolar? Go back up and look. Carbon's 2.5, oxygen's 3.5. So it's polar, which means we'll have a dipole between each carbon and oxygen. The electrons will get pulled toward the oxygens, not to the carbon. Right? Like that kind of a direction. And we'll have the same one on the other side. I'll drop below just so they don't get confused. But now what happens if we add those up? Let's add those vectors together. We'll take this one And then we'll put the other one, we'll start at the tail. And we'll go this way. Those are the same, let's try to make it a little bit nicer. If those are the exact same length, because carbon oxygen is carbon oxygen, what happens to those two vectors when they're added together? They cancel. So we end up with nothing. You got the equal amount this way, and then the same amount this way, you end up where you started. So carbon dioxide is actually non-polar. It has polar bonds in it. The carbon-oxygen bonds are polar, but they cancel each other out. And so the overall molecule becomes non-polar. Another way of thinking about that is when carbon dioxide goes in solution, the molecules around it kind of only see a symmetric lump. They don't really see that difference. And so it acts non-polar. So we would say that carbon dioxide does not have a dipole moment and is actually a non-polar molecule.
Is it because the electronegativity is stronger? The more it gets stronger, the more it becomes like kind of starts.
It actually has to do with the number of groups around the center. So one thing we didn't draw is that oxygen has a couple non-bonding electrons connected to it here. And those take up space too, so they kind of push the other hydrogens down. Whereas this carbon doesn't have any extra stuff around the middle, so they can come back out to straight. It's that kind of a thing. Let's try another one. This is ammonia. Now ammonia kind of has a three-dimensional structure. I'll try to draw it best I can. It's a pyramid with the hydrogens coming down and the nitrogen on the top of the pyramid. So first question is, does it have polar bonds? Are nitrogen-hydrogen bonds polar? So we can go back to the chart and figure that out. And then do they add together to make an overall polar molecule?
Yeah.
So how do you know that?
Because nitrogen is not next to oxygen, oxygen is
Right,
combined.
right. So we're going to expect that nitrogen-hydrogen bond to be polar. So then if a nitrogen-hydrogen bond is polar, is that overall molecule polar, or do the polar bonds cancel each other out in different directions? What do you think?
I think it's polar,
Why?
but I don't know. I'm just looking at the example from the carbon.
The carbon dioxide?
Carbon dioxide. There you go. How it's one extra, I'm assuming that it kind of like throws it off a little bit.
Okay. Well, what we can do is we could draw it and try to figure that out. So in each case, we have a polar bond that goes from the hydrogen to the nitrogen. And this one's a little tricky because we have to think about it in 3 dimensions. But all of those arrows are pointing up, right? So actually the horizontal components of them will all cancel because you've got them pointing in all 3 directions, but they're all pointing up. So the horizontal components will cancel, but the vertical components are still there since there's nothing pointing down to counteract that. So the overall dipole in ammonia is actually also straight up.
So that's supposed to be like a pyramid. 'Cause it's
Right.
Okay.
Right. Yeah, so this is kind of like a pyramid. Like that kind of a shape. And so if you have everything pointing up, then the overall direction is going to be kind of straight through the top there, if you add up all those little directions. So we would say that ammonia is overall a polar molecule because its individual bonds add up to make an overall polarity. Okay, the last part of this then is, why is this important? Why do we care whether or not a molecule is polar? Well, we care because it influences the behavior, the physical properties of these substances enormously. For instance, let's look at some Let's look at some melting points. We remember what melting points are, right? Temperatures that stuff melts at. What's the melting point of water? Zero degrees C, right. And do we call that polar or nonpolar or ionic? Did we determine that water is a polar molecule? Yeah, it is, right? Yeah. So water is a polar covalent molecule. What about, let's take fluorine. It's about the same size, F2. Is fluorine polar or nonpolar? Nonpolar, why? Yeah, because you've got an F and an F. So there's no difference in electronegativity there, right? It's the same, 4 and 4. So that would be nonpolar covalent. And its melting point is minus 220 degrees C. Big difference, right? And then we'll look at one more. Sodium chloride. How would we describe that? That's going to be a third category, not polar or nonpolar, but what do we call that kind of a compound? Ionic, right. So this is going to be our more extreme side of the scale where the electrons are transferred to chlorine. And the melting point of sodium chloride is 801 degrees C. So we've got pretty big differences here. You want to try to explain these anyway? What's going on? Why are the melting points so different for things roughly the same size?
Oh, I see now. Is it because of the, well, first off, it's charge, but because of the fact that it's electronegativity on, or?
Yeah, it kind of relates to all the stuff we've been talking about. We can see that the more separation we have in that electrons, like if they're ionic versus polar covalent versus nonpolar covalent, the more separation we have, the tighter everything's held together, which is why those melting points change so dramatically. So let's talk a little bit about what those forces are.
So if the stronger the bond, the longer it takes to melt.
Well, be careful about saying bond. In an ionic compound, that's probably true. But in a covalent compound, it's not the bonds that are breaking down, right? Because when you melt ice, you don't break the hydrogen and oxygen, but you do separate those molecules a little bit. So that's the forces that we're going to talk about now. And this is why we call them forces instead of bonds. We'll keep that bond word for the molecules, like inside a molecule, covalent bonds, sharing electrons. We'll talk about forces as being between molecules. So we're going to talk about two categories of forces. The first one is what we call dipole forces or dipole attractions is how the book puts it. In a dipole attraction, you have these polar molecules aligning with each other minus to plus. So if we take HCl, anybody remember what's the charge separation here? Which side has the partial positive, which side has the partial negative?
Yes. Hydrogen has plus.
Yeah, hydrogen's got our partial positive, chloride's got our partial negative. So an HCl molecule can find another HCl molecule and you see negative on one side, positive on the other side, they can have an attraction to each other, plus to minus, and kind of hold each other together. And this is how polar molecules attract each other. So they're not sharing electrons or anything. There's just a partial negative here and a partial positive here, and they're coming together and kind of being close to each other. The same thing happens with water. We have partial minus and a partial plus. And we can set up this network with another water molecule so that the pluses and the minuses start to line up. And indeed, this is how you form a framework of ice or of just the attractive forces in water. So in this way, these polar molecules can hold each other together in a way that nonpolar molecules really can't. And this is what's responsible for this big difference in melting point, which is also a difference in boiling points, by the way. Translates the same way. It's these attractive forces that are being weakened or broken when we melt or boil something. We don't actually break the covalent bonds, we break the forces between molecules. And so the stronger those forces are, the harder they're going to be to break, the more energy they take to break, and the higher temperature you need to actually break them. Now, just to make things a little bit more confusing, not that I want to, but sorry. When you have three specific types of bonds, HO bonds, HN bonds, and HF bonds, can form something called hydrogen bonds. Now, this is a terrible term. Remember I said we were going to reserve bonds for talking about sharing electrons inside a molecule? A hydrogen bond is not a bond in that way. It's not a covalent bond. It's a dipole-dipole attraction between hydrogen and another molecule. The fact that it's called a hydrogen bond is confusing, and I wish we could call it something else, but that's what it's called. All right, so we'll just have to kind of keep that straight. So this interaction that we're showing here between an oxygen and a hydrogen is actually what we refer to as a hydrogen bond. Now it should be called like a hydrogen force or a hydrogen attraction or something like that, so that it's less confusing and we don't mistake it for an actual covalent bond, but it's called a hydrogen bond.
And it applies to those, above is hydrogen chloride.
That's right. So it only applies for these three, which means this is not a hydrogen bond. This is simply a dipole-dipole attraction. You need oxygen, nitrogen, or fluorine to actually have a hydrogen bond. And those are particularly strong. The reason they're particularly strong is that oxygen, nitrogen, and fluorine are the most electronegative elements. So they have the biggest separation in charge between hydrogen and the element, the biggest, then they make the biggest dipole, the strongest dipole. That's why things like water have special properties that other things don't. For instance, water has a much, much higher melting point than HCl. HCl's melting point, we'll add that to the list here, is minus 115. So a much lower melting point. So we'll change our words a little bit. This is polar covalent with hydrogen bonds. And this is polar covalent with dipole-dipole attractions. So that's the difference. When you have that hydrogen bond with one of those three elements, nitrogen, oxygen, or fluorine, you have much, much stronger attractive forces. All right. Good so far? It's a lot of stuff.
Yeah.
I know. All right. The last bit is to talk about what happens in the molecules that don't have these things. So if you think about something like, remember we said things made of carbon and hydrogen don't really have any polar interactions. So that would be things like fossil fuels, solvents, organic solvents, hexanes, gasoline. They're held together by something, right? Because those are liquids or solids. Things like waxes are all made of carbon and hydrogen, but they clearly are held together. So they have to be held together by something. The other type of force is called dispersion forces. And these are the types of forces that hold nonpolar compounds together. If you have something like hydrogen, for instance, there's our electron cloud. Remember we said that the electrons would be perfectly evenly shared around the hydrogen. And that's true. From a statistical standpoint, the electrons could be anywhere in that cloud at any time. But from an actual physical standpoint, the fact is that sometimes the electrons will be on one side, sometimes they'll be on the other side, just by chance. If I ask two of you, I'm not going to, if I ask two of you to get up and just start running around the room randomly. You want to try? Okay. We can have two people, and let's say we let them run around the room randomly for like 5 minutes. Would be a good use of class time, I think. If we took a video of that, and we kind of averaged that 5 minutes together, they would, on average, be evenly spaced around the classroom, right? Assuming they took totally random paths. But if we took a snapshot of any given second, the two people could be over here, or one could be here and one could be over there, or both of them could be over there. So that's kind of what's happening here. In individual instances, the electrons might find themselves a little bit more on one side than the other, and that will lead to a very slight, very temporary separation of charge. So at any given time, there might be a little bit of positive over here and a little bit of negative over here. And that's actually enough to start holding these molecules together. That is induced dipole. They're these temporary dipoles that just kind of pop up just because electrons are moving around and sometimes they're not perfectly evenly spaced. So you have these induced temporary dipoles where it will start packing kind of together, and that's actually enough to hold these things together. So the strength of the forces is completely dependent on the size of the molecule. The larger the molecule, the more closely they can pack together and induce each other's dipoles, and the stronger they'll be held together. And just for an example, so water boils at about 100, right? Well, at 100. Water boils at 100 degrees C. If we're talking about a carbon-hydrogen compound, we have to get all the way up to 6 carbons and 14 hydrogens, so C6H14, before we get a nonpolar molecule that starts to have a similar boiling point as water. So water is this tiny molecule, one oxygen and 2 hydrogens, has the same boiling point as a huge 6-carbon chain with a bunch of hydrogens all around it, because the hydrogen bonding forces are so much stronger than these induced dipole or dispersion forces. And this will allow us to kind of predict what types of forces are present, and then also predict how high the boiling points or melting points will be. So I'm looking for an example. Let's look at some examples here. So how I would ask you about something like this. I'm going to give you a list of a few compounds here. I want you for each to determine the major intermolecular attraction in a sample of that. And then take a guess as to which one would have the highest or lowest melting points. So let's say we've got so we got 4 compounds here. What is the major attractive force in the first one? There's a couple, well, that's an element. What of those forces? So are we going to have polar dipole forces? Are we going to have hydrogen bonding? Are we going to have dispersion forces? Or are we going to have ionic forces? No. So first of all, is this an ionic or a covalent compound? Do you think? Ionic or covalent? It's covalent. How do you know? Guessed. Okay. Anybody want to? It is covalent. Anybody want to?
Yes. Hydrogen, oxygen.
Right. Yeah. So we don't see metals here. Doesn't mean that you can't have ionic compounds that don't have metals, but in this case, we don't see any organic ions either. So this is going to be a covalent compound. Now, do you expect it to be polar or nonpolar?
I think it's gonna be
Why do you think it's going to be polar?
because carbon and oxygen, especially oxygen, has the highest potential.
Yeah, so that's a reasonable guess. Now, those of you who are kind of like, well, I don't know if it's polar or not, you're also kind of right, because we really need to know the shape if we're going to determine the polarity of the molecule, right? We need to look at the polar bonds and determine the shape. So you can't always determine just by looking at a formula like this if something is polar, but you can guess that it probably will be because of the carbon and the oxygen. So let's look at the shape of this molecule. It's a little bit complicated. It's got a carbon with 3 hydrogens kind of in a pyramid, and then an oxygen and another hydrogen coming off like that. We know carbon and hydrogen don't have any dipole there. There's no polarity between carbon and hydrogen. So our polarity is going to be up to the oxygen between these two. And so, in fact, it will have that polarity because it's not perfectly evenly balanced on each side. You can see there's some asymmetry, and there's going to be a negative part over by the oxygen. So we would expect this molecule to be polar. And importantly, we'll notice that it has an OH bond, which means it can do what? Yeah, it can form hydrogen bonds. Which are nice, strong interactions. So we'll expect hydrogen bonding or that particular thing to be the basis for the intermolecular forces or the forces between molecules in this compound. This is methanol, by the way, the name of this. All right. So, all right, so next one, HBr. What do you think about that one? We might have to go back and check out our chart here. So hydrogen's 2.1, bromine's 2.8, which means this is going to be also polar. Not as polar as, say, HCl, and can't do hydrogen bonding, but could still have some dipole-dipole forces, some attractions. So we would expect this one to be something like this, with a slight negative toward the bromine. Difference in electronegativity is about 0.8, I think. So a slight difference in some polarity. What about NaCl? There's a better word for it.
Oh,
Ionic. Polar kind of assumes covalency. So we're gonna call this one ionic. But if you look at the structure, what it really is very, very, very strongly polar. A full positive on the sodium, a full negative on the chlorine, no electrons shared at all. Right, so very strong attractions there. And then finally, what about C2H6? This molecule is called ethane. Looks like this. So this is going to be nonpolar. How do you know? There's the symmetry there, and also there's not even any polar bonds here. Carbon and hydrogen don't have a significant difference in electronegativity, so we say that they're basically the same. There should be no particular dipoles or areas of polarity coming up in here. It also means nonpolar, that this is going to be controlled by what we call dispersion forces, those weak temporary forces that hold molecules together.
is carbon like 2.5?
Yeah.
But how come like the hydrogen and bromine it's like bromine is like 2.8?
Right.
It's so by 2, like by 2.
0.3, yeah, it's considered significant enough. So, but you're right, it shouldn't be that big of a difference. So we might say that HBr is weakly polar. But actually, if you think about it physically, well, we'll get to that in a minute. So now we can actually rank these. Let's say we want to rank them by boiling point. Which one of these would you expect to have the highest boiling point based on what we just said?
NaCl.
Probably the NaCl, right? The strongest forces, the strongest attractions. The strongest attractions would be in the NaCl, those strong ionic attractions.
And I figured that too, but just out of curiosity, so I'm assuming some people would be confused with the CHM, mainly because it has this hydrogen bonds are really, really strong as well. So
Yeah, but not nearly as strong as the ionic forces.
really,
Yeah. So if we go back up to these melting points, something with really strong hydrogen bonds like water freezes at 0, but something with ionic forces freezes at or doesn't melt until 800 degrees. So big difference. All right, what do you think comes next? What's the next highest boiling point? Yeah.
CH3OH.
Okay, why? Right, it has those next strongest forces. Then what?
HBr.
Probably HBr. And finally, C2H6 with the weakest forces. And if we look at how we experience these at room temperature, this makes sense. NaCl, we know, is a solid at room temperature, right? Salt, solid. Methanol is a liquid, clear liquid at room temperature. HBr is also a liquid, actually. And then C2H6 is a gas, ethane gas. So we did that just by looking at the structures, thinking about the forces, and ranking them accordingly. And they're ranked based on the strength of their intermolecular forces, or the forces between molecules. All right. Questions about that? All right, let's go over the steps one more time of how you decide this. So first, you're going to figure out the polarity, figure out what kind of forces are involved. That's going to require knowing the shapes. Now we're skipping the part about knowing the shape, so I'll always tell you the shape if you need it. Sometimes you will, sometimes you won't. And then we can rank them based on the strength of those intermolecular forces, the strength of how the particles are attracted to each other, how the molecules are attracted to one another. And that will give us a ranking of boiling point, ranking of melting point. We can also make some conclusions in here about solubility. So something that dissolves in water needs to have similar intermolecular forces to water. Water uses hydrogen bonds. So things with hydrogen bonding, or actually other polar things, are going to dissolve well in water, whereas things that cannot be polar will not dissolve well in water. Will keep to themselves. So there are some things we can do with this. We'll get into this more in a couple chapters when we talk about solutions, but this is a good introduction to it. So, questions about that? All right, that's a good place to stop. So let's we'll start upstairs at 2 with lab 6. There's no report due today because we didn't have lab last week, but please have your pre-labs, and I've got all your old labs, so I got to remember to bring them to give them back to you.
The quiz gonna go up for each time.
The quiz, we'll stick with just the naming for the quiz.
Okay. The 3 different types of naming.
Yeah. So the quiz will be 100% names. Naming, yeah.
We're doing lab 5 or lab 6? Lab 5.
5, yeah. We're on chapter 6. We just finished 6, lab 5.